So now we're going to work through some examples of electron configurations, assigning electrons to orbitals. We're going to write these two ways, spectroscopic notation and orbital diagrams. The orbital diagrams contain more information than spectroscopic notation. So if we take the element hydrogen. Hydrogen is the simplest element on the table because it only has one electron to assign to an orbital. Hydrogen is found in the S block of the periodic table, and it's found, remember the S block, you start counting at 1, so hydrogen is the first row in the S block. S block starts at 1, so the orbital that the periodic table is telling you where the hydrogen electron is going to go is called the 1s orbital. You write a superscript to the right of the orbital, and that tells you how many electrons are in that orbital. So in the case of hydrogen, we only need one electron, so you would read this 1s1. That is the spectroscopic notation of the hydrogen atom in its ground state. When the electron is in the lowest possible energy level, it would exist in the 1s orbital. The orbital diagram gives you more information. We know it's going to end up in a 1s orbital, and we're going to write that 1s orbital as a little box or as just the bottom line of the box. So this line represents the orbital, and we know that's called the 1s orbital. 1s is also the name of the subshell. And we're going to talk in more detail later about the subshell, but the 1s subshell contains one orbital. Hydrogen has one electron to fit into that orbital, and the convention is the first electron that goes into an orbital is assigned a spin value of positive 1/2, which is drawn as the up arrow. So this is the orbital diagram for, not helium, that's the orbital diagram of the hydrogen atom. Helium has 2 electrons. And you find helium on the periodic table. It's way over on the right, it's in group 18, which looks like it may be part of the P block, but it still is part of the S block. And it still is in the first row that you hit in the S block. So helium, also, its last electron will end up in the same orbital as hydrogen. Remember, an orbital can hold a maximum of 2 electrons, so 1 electron for hydrogen. Helium has room for its second electron in that same 1s orbital. The orbital diagram, here is the first electron for hydrogen. Helium has a second electron. It has to go in spin pointing down. The second electron is assigned a spin value of negative 1/2. So the orbital diagram of helium shows 2 electrons in the 1s orbital, and that 1s orbital is part of the 1s subshell. Atomic number 3 is lithium. 3 electrons for lithium. Lithium is also found in the S block of the periodic table, but notice it's in the second row down. And when you go down a row, the quantum number n increases by 1. So the last electron for lithium will end up in the 2s subshell. We know that the 1s subshell, the 1s orbital, was completely full with 2 electrons for helium, so we can't put the third electron into that same orbital. Dropping down a row tells us we're no longer in the 1s, we're in the 2s, and we need 1 electron in that 2s to give us the electron configuration for lithium. The orbital diagram, the first 2 electrons look just like helium's, and then we have the 2s subshell that has one orbital in there, and for lithium we write the electron with the spin pointing up. Beryllium is right next to lithium, 4 electrons total. It will also end up in the 2s subshell where the last electron is. So beryllium has an electron configuration of 1s2, 2s2. The orbital diagram: the first 2 electrons fill up the 1s subshell, and the second 2 electrons fill up the 2s subshell. Boron with 5 electrons is the first place where we hit the p block of the periodic table. And you have to remember that the first row in the p block is not the 1p, because p's start counting at 2, so this will be in the 2p subshell where the last electron goes. First 4 electrons look just like beryllium's, and now we hit the 2p subshell. The 2p subshell will have a total of 1 electron in there to give us a total of 5 electrons. The orbital diagram is a little bit different than what we've seen before. The first 4 electrons match up for beryllium, and now in the 2p subshell, remember p orbitals have 3 allowed orientations. That means there are 3 orbitals within that 2p subshell. So the first electron that we're going to put into that 2p subshell goes in spin pointing up, and the convention is you fill from left to right. So boron has 1 electron in that 2p subshell. That last electron, we knew that was where it was going to be from the periodic table. Carbon is right next to boron. It has 6 electrons. Spectroscopic notation doesn't tell us very much. It just tells us that the 2p subshell contains a total of 2 electrons. You don't see what that really means until you draw out the orbital diagram. So the first 4 electrons fill up the 1s and the 2s subshells. In the 2p subshell, we had 1 electron for boron. Now we need to apply Hund's rule. The second electron into the degenerate 2p subshell, which has 3 degenerate orbitals, has to go into its own orbital rather than pairing up. So this is the orbital diagram for carbon. If you keep going all the way to the end of that 2p subshell, you'll hit neon. Neon has a total of 10 electrons. The 1s is full, the 2s is full, and the 2p subshell is also full. It has 6 electrons in there. The orbital diagram: 1s is full, 2s is full, 2p. I'm still going to follow Hund's rule. If I put in 1 electron at a time, if I stop right here, I would have the picture, the orbital diagram for nitrogen. If I add 1 more electron, that would be for oxygen, 1 more for fluorine, and then finally 1 more makes neon.